Welcome to this explainer. Today, we're taking the absolute chaos of the physical world and transforming it into the exact, precise science of physics. Let's jump right in.
Here's our roadmap for today. We're looking at why we need measurement, the language of units, the global SI system, measuring the extremes, and we'll wrap up with the tools for ultimate precision.
Kicking things off with Section 1, Why We Need Measurement, or as I like to call it, Solving Everyday Chaos.
I mean, think about it. What happens if you walk into a market and ask for 2 liters of potatoes? The vendor's going to look at you like you've completely lost your mind, right? Or imagine telling someone, hey, my height is 6 kilometers, or my weight is 80. Without giving a unit, it's practically impossible to understand. In physics, which is the exact science of nature, guessing just doesn't cut it. We desperately need precise standards.
And this, right here, perfectly illustrates the problem. Let's say you try measuring a wooden board using pens or pencils. That measurement is going to change every single time you sharpen the pencil, or if your friend happens to use a totally different sized pen. That is a classic non-standard unit. Standard units, on the other hand, like using a meter, provide absolute, constant accuracy. It's universally accepted, and it literally never changes no matter who's doing the measuring.
So the crucial takeaway is that a physical quantity always requires 2 things: a numeric magnitude and a standard reference unit. If you say 5 kilograms, 5 is your number, the magnitude, and kilogram is your standard reference unit. If you're missing either piece, your measurement is completely meaningless. And obviously, you can't measure length and just slap a seconds unit onto it.
Moving right along to Section 2, the language of units, building the rules of physics.
Now that we know we actually need units, let's look at how the physical world breaks them down into 2 really interesting categories. On one side, you have fundamental quantities. Think of these guys as the independent bosses. They don't depend on absolutely anything else, things like length, mass, and time. On the other side, we've got derived quantities. These are the structures you build by combining those fundamental units. Like calculating area by multiplying length by length, or figuring out speed, which is just meters divided by seconds.
Which brings us to Section 3, the global SI system, a universal language.
So, back in the day, before standardization, things were a mess. A British engineer using the FPS system would be calculating with feet and pounds, while the French scientist using the CGS system was over there working with centimeters and grams. Imagine the incredibly costly mistakes that caused in international trade. Actually, the only thing everyone somehow seemed to agree on was measuring time in seconds. It just proves how desperately the world needed a unified system.
To finally fix this chaos, the International Bureau of Weights and Measures created the SI system, officially standardizing 7 fundamental units for the entire globe. We've got the meter for length, the kilogram for mass, and the second for time. Then there's the Kelvin for temperature, the ampere for electric current, the candela for luminous intensity, which basically measures brightness, and the mole for the amount of substance. Literally everything else in physics is built straight from these 7 pillars.
But listen, you have to treat the rules for these units like the unbreakable laws of the physics universe. There's a very strict way to write them out. If a unit symbol is named after a famous scientist like Newton or Ampere, it gets a capital letter. But if you're writing the full name out, it always starts with a lowercase letter, so it's a lowercase n for Newton. And this is a big one. Symbols never take a plural form. You write 10 kilograms, never ever 10 kilograms.
All right, Section 4, measuring the extremes from atoms to stars. Our everyday meters and kilograms are great for buying groceries. But what about this? 3.08 times 10 to the power of 16 meters. That absolutely mind-blowing number is just 1 parsec. We need a unit like this because measuring deep space in standard meters is, well, it's pretty much impossible for our human brains to even comprehend.
The scale that physics operates on is just wild. Whether we're zooming way out to a light year, which is the massive distance light travels in a single year, or zooming all the way in to the microscopic Fermi of a subatomic particle down at 10 to the negative 15 meters, physics constantly has to adapt its units just to make the math manageable. We even use the astronomical unit, or AU, simply to represent the average distance from the Earth to the Sun.
And that leads us to Section 5, Tools for Ultimate Precision, Zooming in on Accuracy.
So let's get practical. When we're dealing with small scales in the real world, how exactly do we measure things without messing up? Well, it all starts with the least count. This is the absolute minimum measurement that an instrument can measure accurately. Why should you care?
Well, if you're buying potatoes at the market, a scale with a least count of 50 grams is totally fine. A little over or under, not a big deal. But if you're buying expensive gold, you definitely want an instrument with a microscopic least count, right down to the milligram. Simply put, the smaller the least count, the higher the precision.
Let's trace our quest for ultimate precision. Step 1 is that standard meter rule you probably used in school. Its least count is 1 millimeter, so it literally can't accurately measure anything smaller than that. When that 1 millimeter ruler just isn't cutting it, we upgrade to Step 2, the vernier caliper, which knocks the least count down to 0.1 millimeters. And finally, for true ultimate accuracy, we bring in Step 3, the screw gauge, hitting an incredible least count of 0.01 millimeters.
The vernier caliper is actually pretty genius. Invented by Pierre Vernier, it's a two-scale system that cleverly breaks down a single millimeter into 10 smaller parts. It works by matching n divisions on a sliding vernier scale with n-1 divisions on a fixed main scale. By figuring out exactly which tiny lines perfectly align across the two scales, we can measure things, like the internal diameter of a small beaker, with perfect 0.1 millimeter accuracy.
But you've got to be careful. If you fully close your vernier caliper and the zeros on both scales do not perfectly match up, you've got a mechanical defect called a zero error. And this can actually be a positive or a negative error. It is absolutely crucial that you calculate and subtract this error from your final observation to get the true reading. If you just ignore it, well, your super high-precision measurement becomes completely useless.
Now, for even more accuracy, the screw gauge relies on a totally different mechanism based on something called pitch. Pitch is the tiny horizontal distance traveled by the screw when you give it one complete 360-degree rotation. The screw gauge achieves that mind-blowing least count of 0.01 millimeters by taking that tiny pitch and dividing it by the total number of divisions on its circular scale.
These instruments are incredibly delicate, though. You have to watch out for a backlash error. This happens because of wear and tear on the internal threads, which is usually caused by abruptly reversing the direction you're rotating it. So the pro tip here is to use these delicate instruments gently, rotating them in one continuous direction. Actually, scratch that. If you force it back and forth, you'll literally strip the threads, create a permanent backlash error, and totally ruin your precision.
And that brings us to a really profound question. How does mastering the precision of these microscopic measurements ultimately allow us to understand the massive scale of the entire universe? Think about it. From buying 2 kilos of everyday apples, to perfectly measuring the 0.01 millimeter thickness of a wire, to calculating the distance to a distant star in parsecs, physics relies entirely on the exactness of our instruments. It kind of leaves us to wonder, what completely new rules of the universe are we going to discover when our instruments become even more precise? Thanks for exploring the science of measurement with me on this explainer. Keep asking questions, and I'll catch you on the next one.